So we have seen earlier what are normal and shear stresses. So normal stress is a stress which is perpendicular to the plane of interest, while shear stresses are stresses parallel to the plane of interest or lies in the plane of interest. So we have posed this question uh, to define a state of stress at a given point. What are the complete specification that we need? So we have to specify normal or shear stresses, or we can call it as stress components on three orthogonal planes to define complete state of stress at any given point. So I have my reference coordinate axis x, y, z in this fashion, and I have three orthogonal planes which are there. So one is x plane, which is perpendicular to x direction, y plane perpendicular to y direction, and z plane, which is perpendicular to z direction. Now, how many stress components are required in order to completely specify state at point stress, or the stress at any point O? Let's say here. So we have seen earlier that any force can be, or any stress which is acting on a plane can be resolved in three components of it. One is normal stress perpendicular to the plane, and two shear components which are parallel to the plane. So we have three stress components for any given plane. Now we have three orthogonal planes which are x plane and z plane also. So we have 3, 3 and 3, which counts to be 9 components. So you need 9 components in Cartesian coordinate system to define to define a stress at any given point O, or to specify completely a state of stress at any point O. Now let's look at how we represent these stress components uh, uh, at any point O. Let's say I have a body which is being subjected to different forces, and which is in a static equilibrium, and I take out one small elemental cube from this body, and I represent this stress components on this small elemental body or elemental cube. So I have this elemental cube. I mark my coordinate axis x, y, z in this fashion, and here now I try to represent what are stress components. What are stress components? So components means normal stresses and shear stresses. So I have three orthogonal planes, and I'll try to represent this shear and normal stresses on this elemental cube. So I have this elemental cube whose area of the faces is so small enough that the change in stress over the face is very negligible. So let's look at how we present these stresses, normal and shear stresses on this elemental cube. So we have sigma yy. So we know that we have seen that sigma denotes normal stress, and it has suffix 2 suffix yy. So the first alphabet or a symbol represents plane on which it acts, while second symbol represents along this direction, means along which direction this stress is acting. Let's understand this using sigma yy. Okay, so the sigma denotes normal stress. That means it must be perpendicular to the plane of interest, while y is representing which plane. Okay, so uh, this is representing a y plane. So here, where is the y plane? The y plane is this is my y plane, which is perpendicular to y direction. So this is y plane, and which is y direction. So this is y direction, which I have defined. Okay, so this is y direction. So this stress is acting perpendicular to y plane, because this is normal stress. So this is perpendicular to y plane and along y direction. So this is my sigma yy. Now shear stress. Let's I have tau yx. So tau denotes shear stress. The first alphabet or symbol here also represents plane on which it acts. So shear stresses lies in a plane of interest, and the second symbol also indicates the direction along which it acts. So tau yx will be this shear stress. So it is in a plane, in a y plane along x direction. So this is x direction, so it is acting along x direction. So this is my tau yx. Now let's look at some other components here. So let's say tau yz. So tau yz is a shear stress acting in acting in a plane y, which this is a y plane, and along z direction, positive z direction. Uh, Now, similarly, let's understand sigma zz and sigma xx. So, sigma represents normal stress. So, this must be perpendicular, and zz. So, the first alphabet is representing which plane it is acting. So, it is acting on a z plane. So, this is my z plane. So, and it is perpendicular to z plane and along z direction. So, the second alphabet is representing z direction. So, it is pointing towards positive z direction. Similarly, sigma xx, sigma represents normal stress. First alphabet is representing which plane? So this is my x plane, this plane is my x plane, and along x direction. So this is x direction, so it is pointing out away or perpendicular to x plane along x direction. So this is my sigma xx. Now let's look at some other shear components. So let's say tau xy. So tau xy is a shear stress in x plane along y direction, whereas tau xz is a shear stress acting on x plane along z direction. Similarly, tau zx is a shear stress acting in z plane. This is z plane along x direction. Tau zy tau zy, it's shear stress acting on z plane along y direction. Similarly, you can have tau yx and tau yz. So these are the stress components which we have represented on the on this elemental cube. So you can I have represented it on on positive y plane, negative y plane, x plane, and z planes. Similarly, you can represent them on negative x plane and negative z plane also. So in all, we have 9 components. Okay, so we have 9 components which are there. So these are 3 components on y plane, 3 components on x plane, 3 components on z plane. So it makes 9 components. So now let's move on further and see what are the sign conventions for this stress components. So I have this elemental cube, and let's now look at what are sign convention. So I have sigma zz, which is acting perpendicular to z plane but go against this z plane. Okay, so this is a compressive stress, and I call it as I mark it as negative. Similarly, if the stress is in a tension or it's a tensile nature, I mark it as positive. Another way of looking at it is that, let's say I have this z plane, I have marked this z plane, and let's say the direction normal to this z plane, let's say this is my direction normal, which is perpendicular to this z plane. Now I can say that if the stress, normal stress, okay, if normal stress is acting along, okay, if it is along direction normal, this direction normal, it will be tensile stress, which is positive, and it's tensile. If it is acting against, okay, against normal, I call it as negative or compressive. Okay, so here in this case, you can see clearly that sigma zz is acting against this normal or opposite to this normal. Then that's why it is compressive. Now, what about shear stresses? So let's say this shear stress. So in shear stresses, you see which plane it is acting. So it is acting on this plane, which is positive y plane, okay, but it is acting in the negative direction, at negative x direction. So let me write it. So this is positive y plane, okay, positive y, but in negative x direction, this stress. So I call this stress as negative, okay, negative tau yx, okay. So this is my negative tau yx, okay. So this becomes negative tau yx. Uh, so and this now let's say tau yz, which is also negative. This is acting on positive y plane but in the negative z direction. So the convention for shear stresses, let's say if it acts along positive direction on positive plane, it is called as positive shear stress, and if it acts along negative direction on positive plane, then it is negative. So let's understand this uh, again with some other examples. So I have this tau yx, which is acting on positive y plane. I have negative y plane. Let me write it also here. So this is my negative y plane, okay. So this is my negative y plane. So if uh, the shear stress acts on positive plane but in the negative direction, it is negative. And if a shear stress acts on a along a negative direction on a positive plane. So these two stresses are acting on a negative along a negative direction, but they are on a positive plane. So they will be negative. But let's say I have a negative y plane, and the shear stress acts in the negative direction, so that will be positive. Let me write it for you. Uh, so let's say if I have a shear stress something like which is acting like this, it is in on a negative plane and negative direction, so this stress will be positive. While if the stress is on negative plane but on a positive direction, so this will be negative here, okay. Similarly, so there is another way of looking at it is we'll come to it. So uh, we'll come to it in the upcoming slides also. So as of now, you can see that the sign conventions for shear stresses is acts along positive direction on a positive plane, so that will be positive. If it acts along a negative direction on negative on a positive plane, it will be negative. Uh, let's say now let me take one more example to demonstrate this. Let me write it. Let's say I have this plane which is negative z plane. Okay, this is negative z plane. Let's say I have a shear stress which is acting along this direction. So this is in the positive y direction. So this will be on a negative z plane, but it is acting along positive y direction. So this will be negative shear stress, negative tau. Okay. Similarly, if the shear stress is acting, let's say this is positive z plane, and let's say I have shear stress which acts along positive x direction. So this will be positive shear stress. Okay. Now we have these 9 components. We have these 9 components of stress, and we have also seen what are the sign conventions for this uh, normal and shear stresses. So which are they? We have seen sigma xx, tau xy, tau xz, tau yx, sigma yy, tau yz, tau zx, tau zy, sigma zz. Now you can see that the diagonal components are your normal stresses, okay, and what are the components of stress which are non-diagonal or other components are your shear stresses. So we have seen how they have been represented. In some textbook, uh, they write it as the shear components. Also, they mention as sigma. So when this, let's say, when I say, let's say, let me write it in terms of mathematics. Let's say I call it as sigma ij. Okay, and when sigma, sorry, let's say this, we have written sigma ij, and uh, when I equal to j, that becomes your normal stress, isn't it? Normal stress. And what are, when I is not equal to j, those are shear stresses. So that is what we have seen over here. So we have sigma xx when I is equal to j, that is your normal stresses. So these uh, diagonal components are your normal stresses. When I is not equal to j, they are shear stresses. In some textbook, now here we have seen x, y, and z. So in some textbooks they use x1, x2, x3. So the stress tensor will be represented as sigma 1 1, sigma 1 2, sigma 1 3, sigma 2 1, sigma 2 2, sigma 2 3, sigma 3 1, sigma 3 2, sigma 3 3. So here also the diagonal components are your uh, normal stresses, and of other components are shear stresses. So sigma 1 1 means it's a stress, normal stress, perpendicular normal stress acting on plane 1 along one direction. Okay, so let's say, let's assume, let's consider this coordinate axis, and then let me write it down for you. So this is my one plane, okay, and this is my x1 direction. So this is sigma 1 1 will be acting perpendicular to this 1 1 plane uh, along one direction. This will be your sigma 1 1. Similarly, you can find out what is sigma 1 3, sigma 2 2, etc. So this represent one and the stress, one and the same thing, uh, as a stress tensor. Okay. Now I have mentioned you that it is a stress tensor. Let me give you a brief introduction about what are tensors. Okay, you can read more about tensors somewhere else, but for our course, let me introduce what are tensors exactly. So before that, let's understand what are scalars. So in scalars, you are aware that they can be defined just by magnitude. It's a mass, distance, temperature, etc. Vectors, you need both magnitude and direction, like let's say velocity and forces. Uh, Scalars, let's say 10 kg, 5 centimeter, 100 degrees Celsius, you don't need any direction, you just need a magnitude. For vectors, let's say for velocity, I need a components along my x direction, y direction, and z direction. So to define a completely this quantity in a vector form. Now tensors, as we have seen, I mentioned about stress tensor. So we have seen that it needs magnitude, it needs direction, and it also needs the plane of application. We have seen sigma xx means a normal stress acting on plane, acting perpendicular to plane x and along x direction. So these are the tensors which need another uh, component to define it as the plane of application. Uh, some of the examples are stress electromagnetic tensor. So let's see stress tensor. We have mentioned that we are taking this elemental cube, and this cube is 3D. So whatever the tensorial quantity representing this cube will must be 3D. So 3D means the stress tensor is of the dimension is 3 here, because it is relating with a 3D object, which is a cube here. So I have this stress tensor which we have defined earlier. Now if you look at this stress tensor, the first row uh, is representing something. What is it representing? It is a plane, or the stress acting on plane perpendicular to x, or acting on plane x, isn't it? So While similarly, you have the stresses which are acting on plane y. Now, uh, if you see this column, it is along x direction, uh, while other two columns are representing the stresses acting along y and z direction. Now, I write this stress tensor again. Now let's say these are 9 components which I have. From that, I would like to find out. I take one component. Let's say tau y z. Now, how many pieces of information that we need? We need two pieces of information. One is uh, plane on which it is acting. Let's say this. So, and one is the direction on which it's acting. So, I need two pieces of information. Let me write it down. So, I need this one is representing your direction. Okay, that is z direction, and this one is representing the plane, so on which it is acting. So I call it as this is a y plane. So I need two pieces of information, one row and one column, to completely identify one component, this component tau yz. So this is called as a rank or order, which is now the amount of information you need to find a specific component. So I need two pieces of information. So this stress tensor has a rank or order as 2. Rank is equal to order. Okay. So what is the order of this stress tensor, or rank of the stress tensor is 2. So we have this stress tensor as rank 2 or order 2, and it has a dimension 3 because it is dealing with a 3D object, that is a cube here. Similarly, you can see that for a vector, I can say that it is of order 1 because I just need one piece of information. Similarly, here I don't need any pieces of information, I just need a magnitude. So scalars are tensor of order 0 or rank 0. Now you can see that there are 9 components. So there is a relationship between your dimension and an order. So you have components is equal to dimension to the power order. Now I have components is equal to here the dimension of this stress tensor is 3 and order or rank is 2. So I have in all 9 components. So let's say I have an electromagnetic tensor over here, and which is of order 2 and dimension 4. So how is order 2? Let's say I want to find out px. So I need only one row and one column to define this, to get this component. So order is 2 and dimension is 4. So how many components? It must have 16 components. Now in general, we have these notations for tensorial quantities. So Vi represents your first order tensor. So I just have put one suffix over here, and it represents the first order tensor. Whereas sigma ij is second order tensor, sigma ijk is third order tensor, and ijkl is a fourth order tensor. Okay, so this is kind of a compliance matrix which we'll be dealing in our course. So with this, I will move on and let's understand the independence of stress components. We have seen there are 9 stress components, but out of which how many are independent. So let's mark this stress components over here. And I have mentioned earlier that this elemental cube is in also must be in a static equilibrium. What is static equilibrium? Summation of all forces must be equal to 0, and summation of moment should be also equal to 0, so as to maintain that body should not accelerate or it should not rotate. It is in a static equilibrium. So you can see that sigma yy is acting on uh, this y plane along y direction, and it is also acting on a negative plane, so it is balancing each other. Similarly, you can do it with sigma xx, sigma zz. I haven't shown sigma zz here, but you just can correlate what you have seen for y plane, plus y plane and negative y plane. Similar things are happening for plus x and minus x, and plus c and minus z plane. So this forces are balancing over here. Similarly, tau yx will be counterbalanced by tau yx in the another plane. So forces are balancing here. Now let's look at what is a moment. Now let's take a moment along z direction. Before that, let me mark the dimensions of this cube as delta x, delta y, and delta z. So now I take a moment along z direction. Let me write it for you. So I take a moment along this direction. Let's set point O over here. Now to find out a moment along z direction, moment will be given by force into perpendicular distance. So now I consider, let's say, tau yx here. Okay. So I have tau yx, which is stress. Now to convert stress into force, what I have to do is I have to multiply by the area of this or this plane. So what I'm let me write it down. So I have tau yx. Okay, I have tau yx. What will be the area of this plane is delta x into delta z, and we should multiply for a calculating moment. We should multiply by a distance. So this will be delta y by 2. So I should multiply it with delta y by 2. Okay. So now similarly, let's look at how the moment is happening. So if I have tau yx, which is also acting on this direction, along this direction. So this also will create a moment along z direction. So you can see that this tau yx giving me a notion of a clockwise notion, or trying to move this element in the clockwise direction. What is that? Let me write it. So I have, let's say, when I draw these components over here, so uh, I have tau yx. So this is my tau yx. Also this is tau yx. So this is giving me a clockwise notation. So I term it as positive moment. Okay. Now there are two components. Okay, tau yx. So I I add it up. This is also giving me positive notion. So I add it up, and so the moment which is making a clockwise motion will be 2. Let me put it here. Let me put it here. So this will be 2, which will be giving me a clockwise motion. Now I have marked over here this term. I have marked this term over here. Similarly, I have tau xy, which is acting on this x plane, and so this tau xy, that is a shear stress acting on this x plane, is causing a moment which is in the counterclockwise direction. Okay, so I will multiply this is a stress multiplied by area of this space and in the perpendicular distance from this point O. Okay, so this is what I have marked, and I have tau xy, which is acting on the negative x plane also, so I multiply it by 2. So this tau xy is giving me, let me write it down, this tau xy is giving me, so this is my x plane, this plane is my x plane, and this plane is my negative x. Okay, negative x, this is positive x, and this is giving me a counterclockwise motion. Okay, counterclockwise. So that's why and these are two shear stresses, so I will put here as 2. So and these two clockwise movement and a counterclockwise movement will balance each other, and you can see here clearly that these terms will get cancelled out. All these terms will get cancelled out. 2 also will get cancelled out, and what you have left with is that uh, tau yx is equal to tau xy. Now this we have proved it here. This is an important result. So like, to have a static equilibrium maintained, you must have this tau yx equal to tau xy. Similarly, we can show that tau xz and tau zx to be equal, and tau yz and tau zy to be equal. So these are very important identities which we got. Now let's look at the stress components. So we have normal components here and shear components over here. So uh, you can see that the shear components uh, are so you have tau xy, I should write it here, and tau yx must be equal. Tau xz and tau zx must be equal, and tau zy and tau yz are equal. So in our how many stress components we have uh, which are independent? So we have first, second, third, fourth, fifth, 5 and 6. So we have in all 6 components which are independent. So if I know tau xy, I can know tau yx also. So we can see clearly that when I know tau xy, I can know tau yx, tau xz. When I know tau xz, I know tau zx also. When I know tau yz, I know tau zy. Okay, so I just need 6 components to know a complete state of stress at any given point. Similarly, you can see that this matrix becomes symmetric. Okay, so I need 6 components, and this matrix remains symmetric in the sense. Let me write it down. So I just need these 6 components to be defined my state of stress: 1, 2, 3, 4, 5, and 6. Okay, so I just need these 6 components, and the rest of them remains. The rest of this I can find it out. So out of 9 components, 6 only are independent. Okay. So with this, I'll stop here.